Welcome to the deep dive. Today, we're venturing into what you might call the engine room of artificial intelligence, optimization.
That sounds about right.
You, our listener, asked us to explore how AI models actually learn and improve. So that's exactly what we're going to unpack today.
Yep.
We've gathered our sources, aiming to give you a really clear, insightful look at this essential process, from the core ideas to the techniques that actually drive AI forward. Our mission really is just to pull out the key knowledge you need to grasp this field without getting totally bogged down in the heavy details.
Right. And, at its heart, optimization is really just a mathematical way of finding the best possible answer to a problem from, well, a whole set of options.
Okay.
And when we talk about AI and machine learning, what we mean is fine-tuning the inner workings, the parameters of the algorithms and models.
The knobs and dials, sort of?
Yeah, exactly. The goal is always to get the best possible performance based on whatever criteria we've set. Think of it like a chef constantly tweaking ingredients to get that perfect dish.
Okay, so how do we actually know if the AI is getting better? How do we measure that improvement?
Good question. That's where objective functions come in. You might also hear them called cost functions or loss functions, same idea.
Right.
These basically give us a number, a quantitative measure of how well the model's doing. They assign a score to different setups, different parameter settings.
So a lower score is better, usually, if it's a cost or loss?
Generally, yes. If we're measuring error, we want that score to be as low as possible. The whole point of optimization, then, is to find the specific settings, the input variables that minimize or sometimes maximize this function.
And doing that directly improves the model's ability to predict things.
Exactly. It improves its predictive capabilities. So the core ideal, we give the AI a measurable target, and optimization is the process of, well, relentlessly chasing that target.
So it's like giving the AI a test, it gets a score, and then optimization is trying to adjust things to get the absolute best score possible on that test.
Precisely. And this whole thing, it can be described formally, mathematically.
Okay.
A typical optimization problem looks something like minimize x fx.
Right.
Here, x is just all those adjustable knobs on the AI model. It's parameters. And fx is that performance score. We want to minimize it if it's measuring error, for example.
Okay.
But often, we also have rules, boundaries we have to work within. These show up as constraints. You might see subject to get x0. Those are inequality constraints.
Like limits we can't go past.
Exactly. Like maybe the model can't use more than a certain amount of memory.
Yeah.
And then you have hjx x00. Those are equality constraints, exact conditions the solution must meet.
So the G and H things are the rules we need to follow while turning the knobs X to minimize the score F.
Yeah, that's the basic mathematical picture.
And this isn't just some abstract math problem, right? This optimization idea is absolutely fundamental to making AI work in the real world.
Oh, absolutely. It's integral. It's involved in practically every stage. From the initial training, where the model learns from data,
right,
all the way to deployment, when it's actually making predictions or decisions out there. It's what allows AI systems to learn effectively, adapt, and ultimately make accurate predictions.
So it affects everything, accuracy, efficiency.
Oh, effective it is overall, yes.
And one really key area where optimization plays a huge role is during model training itself, isn't it?
Exactly that. When we train an AI model, we're essentially trying to find the best settings for its internal parameters, things usually called weights and biases.
Okay.
The goal is to minimize the discrepancy between what the model predicts and the actual data we showed it. That difference is what the loss function measures.
Right, the error score again.
Precisely. And algorithms like gradient descent are key here. They work iteratively, adjusting the parameters bit by bit, always taking steps in the direction that reduces that loss score.
So step by step, getting closer to the best predictions.
That's the idea. The better we minimize this loss, the more accurate our model becomes, and hopefully the better it generalizes to new data it hasn't seen before.
And there are ways to make that process even better.
Oh, yes. We use clever tricks. Things like learning rate scheduling, which adjust how big those steps are that the algorithm takes.
Okay.
And momentum, which helps it keep moving in the right direction, sort of smoothing out the journey and avoiding getting stuck in little bumps in the road.
Okay, so training fine-tunes the internal settings. But you mentioned we also set things up before training starts. What about those external settings? That's hyperparameter tuning, is that right?
You've got it. Hyperparameters. These are the model's external configuration settings. They aren't learned directly from the data during the main training loop.
Like what sort of things?
Well, things like that learning rate we just mentioned. The number of layers in a neural network, or how many neurons are in each layer, the type of activation function used, how much data we process at once, that's the batch size, or even how strongly we try to prevent the model from just memorizing the training data, which is called regularization.
Right.
Optimization techniques are crucial here, too, for finding the best combination of these hyperparameters.
So you optimize the optimization settings in a way.
Kind of, yeah.
Yeah.
We want the set of hyperparameters that gives the best performance on data the model hasn't been trained on, usually called validation data.
And how do you find that best set?
We use different methods. There's grid search, which is quite brute force. It tries all combinations in a predefined range.
Sounds slow.
They can be.
Yeah.
So there's also random search, which just samples random combinations.
Yeah.
Often works surprisingly well.
Huh.
And then more sophisticated approaches like Bayesian optimization, which learns from past attempts to make smarter guesses next time, or even evolutionary algorithms.
Wow, okay.
Getting these hyperparameters right can make a huge difference. Big jumps in accuracy, better reliability, sometimes even speeding up the training itself.
This is giving me a great picture. Maybe we could zoom out a little. Look at the different kinds of optimization problems we run into in AI.
Excellent idea. It helps to categorize them. One big distinction is between continuous and discrete optimization.
Okay.
In continuous optimization, the variables we're adjusting the parameters can take any value within a range. Like the weights in a neural network, they're usually real numbers.
Right.
Techniques like gradient descent are really well suited for these.
And discrete.
Discrete optimization deals with variables that can only take values from a limited, finite set, maybe choosing between different types of components or something like that. We won't go super deep into it today, but it's good to know it exists.
Okay, continuous versus discrete. Got it. What's another way to slice these problems?
Another important way is constrained versus unconstrained.
Ah, like the rules we talked about earlier.
Exactly. A constrained problem means the solution must satisfy certain conditions. Those gx less than or equal to 0 or hx equals 0 things.
Like the memory limit example.
Right. An unconstrained problem doesn't have those specific restrictions on the solution itself.
Yeah.
And then there's a really, really crucial distinction in AI.
Which is?
Convex versus non-convex optimization.
Convex versus non-convex. Okay, that sounds important. Why is that such a big deal?
It's fundamental because it tells us how hard it's likely to be to find the actual best solution, the global optimum.
Okay.
In convex optimization, the objective function and the feasible region, the space of allowed solutions, have this nice, smooth sort of bowl shape.
A bowl.
Yeah, think of a simple bowl. No matter where you start inside it, if you always go downhill, you'll eventually end up at the single lowest point at the bottom.
Ah, I see.
The amazing thing about convex problems is that any local minimum, any point that looks like the bottom in its immediate neighborhood, is the global minimum. There's only one bottom.
Guaranteed.
Guaranteed. And we have really efficient algorithms to solve these, like interior point methods, gradient descent works well here too, and the simplex method for linear programming.
Where do we see convex problems in AI?
Things like support vector machines, logistic regression, some core machine learning techniques fall into this category. The key insight: guaranteed global optimum found efficiently.
Okay, so convex is the easier path, relatively speaking. What about non-convex?
Non-convex is where things get, well, much trickier. Here, the objective function can look like a rugged mountain range. Lots of hills, valleys, peaks.
So many places that look like the bottom locally.
Exactly. Multiple local minima. Points that seem like the best solution if you only look nearby, but they aren't the lowest point overall in the entire landscape. The feasible region might also be complicated.
And finding the true lowest point, the global optimum, is hard.
Much harder. Because our algorithms can easily get stuck in one of these local valleys thinking they've found the best solution when a much better one exists somewhere else. That's a core difficulty.
And this is common in AI.
Extremely common, especially when training deep neural networks. The loss surface, that landscape we're trying to navigate, is typically highly non-convex, full of local minima and also things called saddle points, which are tricky flat regions.
So how do we deal with that?
We use more advanced techniques. Stochastic gradient descent, often with momentum, helps bounce things around a bit. Adaptive learning rates like Atom adjust the step size cleverly. And sometimes we use heuristics, like genetic algorithms or simulated annealing, to try and explore more broadly and hopefully find a good solution, even if we can't guarantee it's the absolute best.
This gives us a much clearer sense of the challenges. So given all these types of problems, what kind of tools, what algorithms do we actually have in our optimization toolkit?
It's a pretty big toolkit. We have a wide range of algorithms, each with strengths and weaknesses. A really fundamental group is gradient-based methods.
Like gradient descent we mentioned?
Exactly. They use the derivatives, the gradients of the objective function, to figure out the downhill direction. Gradient descent and its many variants, SGD, ATOM, RM's prop, they're the real workhorses for training most machine learning models. They work well when the function is differentiable and relatively smooth.
Right, makes sense. What else is in the box?
Then you have evolutionary algorithms. These are inspired by, well, natural evolution.
Survival of the fittest for solutions.
Kind of. They're great for complex problems where maybe we don't have gradient information, or the function is messy and non-differentiable. Genetic algorithms are a classic example.
How do they work? Briefly.
They maintain a population of potential solutions. Over generations, the better solutions are more likely to reproduce, combining parts of good solutions, crossover, and introducing random changes, mutation. It's a powerful way to explore a really wide search space, what we call global search. Good for discrete variables, too.
Okay, gradient-based for smoother paths, evolutionary for rugged exploration. What else?
We also have heuristic and metaheuristic methods. Heuristics are basically smart rules of thumb. They give us good enough approximate solutions when finding the perfect one is too hard or takes too long.
And metaheuristics.
Metaheuristics are like strategies that guide those heuristics to search more effectively. Think of simulated annealing. It's inspired by cooling metal. It sometimes accepts a worse solution temporarily.
How would it do that?
To try and jump out of a local minimum, it's like shaking in the system a bit to avoid getting stuck too early. Then there's particle swarm optimization.
Inspired by birds or fish?
Yeah, how flocks or schools move together.
Right.
And ant colony optimization, mimicking how ants find efficient paths to food using pheromone trails.
It's amazing how much inspiration comes from nature.
It really is. Then, of course, we need ways to handle those constraints, the rules. So we have constraint optimization algorithms.
How do they work?
Techniques like Lagrange multipliers or penalty and barrier methods. They essentially modify the objective function to penalize solutions that violate the constraints. They steer the search towards valid solutions. Things like sequential quadratic programming are also used here.
Okay. And if we need more speed or precision and the problem allows it?
That's where second-order methods can be useful. They use not just the gradient, the first derivative,
Yeah.
but also the Hessian matrix, the second derivatives.
What does that tell us?
It gives information about the curvature of the landscape. This can lead to much faster convergence towards minimum. Newton's method is the classic example. Quasi-Newton methods like BFGS try to approximate the Hessian more cheaply. Conjugate gradient is another powerful one. The trade-off is usually higher computational cost per step.
Right. More information, but more work to get it. We're building quite a list. What if we can't even calculate derivatives? Say, the function is a total black box.
Good point. For those situations, we have derivative-free optimization methods. These are designed for functions where we can query the output for a given input, but we don't know the underlying formula, or it's just impractical to differentiate. Pattern search methods are one type. They explore points systematically around the current best solution.
Okay. And finally, circling back to those nice convex problems.
For convex optimization, where we have that guaranteed global minimum, we have specialized, highly efficient algorithms. Interior point methods are very powerful. There's also the ellipsoid method, subgradient methods for non-smooth convex functions, and dual algorithms. They offer reliability and efficiency.
And for the tough non-convex ones?
We rely on non-convex optimization strategies. Stochastic optimization, using randomness, often through mini-batches, is key here, partly because it helps escape those local minima and saddle points we talked about.
It really sounds like there's a tool for almost any optimization scenario. But even with this impressive arsenal, there must be common challenges, right? Pitfalls we run into when actually trying to optimize AI models.
Oh, absolutely. Despite all these algorithms, we definitely face recurring hurdles. One huge one, as we've touched on, is getting stuck in local optima.
Right. The fake valleys.
Exactly. Especially in non-convex problems like deep learning. The algorithm finds a solution that looks good nearby, but isn't the best overall. We try to mitigate this with things like simulated annealing, genetic algorithms, or using momentum-based optimizers that can help roll through smaller dips.
Yeah, sounds like a major headache. What's another common one?
Another big challenge, particularly in very deep neural networks, is the vanishing and exploding gradients problem.
Vanishing and exploding. Sounds dramatic.
You can be. Vanishing gradients mean the signal, the gradient, gets incredibly tiny as it propagates backward through the network layers. This makes it really hard for the earlier layers to learn anything useful. The updates become minuscule.
So learning stalls.
Pretty much, for those early layers. Exploding gradients are the opposite. The gradients become enormous, leading to wild swings in the updates and making the training process unstable. You can just blow up.
How do we fight those?
We have techniques. For exploding gradients, a common trick is gradient clipping, basically capping the gradient size if it gets too large. For vanishing gradients, using activation functions like ρLU and its variants helps, as does architectural changes like residual networks, ResNets, which provide shortcuts for the gradient to flow back more easily.
Okay, gradient troubles. What else makes optimization tough?
High dimensionality. That's another big one.
Meaning too many parameters or features?
Exactly. When models have millions, even billions of parameters, or the input data has thousands of features, the optimization landscape becomes incredibly complex and vast. Just searching it effectively is computationally expensive, and it's harder to even understand what's going on.
So how do you cope with that scale?
Several ways. Feature selection to prune irrelevant inputs beforehand. Regularization techniques, which encourage simpler models by penalizing complex ones, using sparse models where many parameters are zero, and designing algorithms that are inherently better at handling high dimensions.
Makes sense. More dimensions, more complexity, and I guess a very practical issue. All this optimization must take a ton of computing power.
You bet. Computational cost is a major constraint. Training state-of-the-art models can take days, weeks, even months on powerful hardware. It's incredibly resource-intensive.
So what are the strategies there?
We relied heavily on things like stochastic optimization, using MIDI batches, processing smaller chunks of data at a time instead of the whole data set at once. That's much more efficient.
Okay.
Also, parallel computing across multiple CPU or GPU cores. Distributed systems that spread the workload across many machines in a cluster. And, crucially, specialized hardware accelerators like GPUs, TPUs, tensor processing units, and FPGAs, which are designed specifically for the kinds of matrix operations common in AI.
Wow, okay. That was a really comprehensive tour through the world of AI optimization. We've covered what it is, why it's so absolutely critical, the different kinds of problems we face, convex, non-convex, constraint, the huge array of algorithms in the toolkit, from gradient descent to evolutionary methods.
Yep, quite a range.
And finally, those common challenges, local optima, gradients, dimensions, costs that keep everyone on their toes.
Indeed. So just to quickly recap the key nuggets for you. Optimization is really the engine of AI learning. It's how models improve by adjusting their parameters based on those objective functions, those scores.
Got it.
The type of problem, especially convex versus non-convex, really shapes the approach and what algorithms work best. We have this diverse toolbox, gradient descent being fundamental, but many others for different needs.
Right.
And lastly, those challenges getting stuck. Gradients vanishing or exploding, handling massive scale, the sheer computational costs, they're always part of the picture and require clever solutions.
Absolutely. And maybe on that note, here's a final thought for you, our listener, to chew on. Considering the sheer variety of optimization techniques we've just discussed, and the challenges that still exist, how might the future of AI be shaped by developing even more sophisticated, more efficient optimization methods?
Interesting question.
Could we see breakthroughs coming from fields we don't normally associate with this, maybe outside math and computer science? And what completely new AI capabilities might pop up once we overcome some of these current optimization bottlenecks, perhaps in really complex decision-making, or creating AI that's truly personalized to each individual?
Yeah, what happens when we get really good at navigating those complex landscapes?
Exactly. Definitely something fascinating to think about. Thanks for joining us for this deep dive.